So I started to learn the theory about to learn the theory of endoscopy by reading Professor Labez's lecture notes, Introduction to Endoscopy. That was really helpful to me. And then at a certain stage of this work I'm going to present, I also refer to Professor Labez's book, Cohomologie, Stabilisation et Changement de Base, for countless number of times. So that was also a great influence. And of course, the topic I'm going to talk about today is a subject that Professor Labez worked on, and his name will also appear several times in the talk. Okay, so I want to tell you about the subject of zeta functions of Shimura varieties. So as the title of my talk suggests, I want to first give you some kind of historical overview, and then talk about some current developments and something to be expected in the near future. Okay, so the starting point of this story is the result of Eichler and Shimura in the 1950s, where they computed the Hasse-Weil zeta function of the modular curve of level gamma naught n, and they showed that it is given by this formula. You have the Riemann zeta function at S times the Riemann zeta function at S minus 1, and then you divide by the product of L functions of weight 2 cusp forms. So F-I-S. So here it's a finite product. So here these Fi's are elements of an eigenbasis of eigenbasis of the space of weight 2 cusp forms of the level gamma naught n. Okay, right. So then the goal is to generalize this such an expression of the Hasse-Weil zeta function in terms of L functions of automorphic representations to the case of Shimura varieties. So generalize to more general Shimura varieties. All right, so we start with the Shimura datum. Gx. And then due to the results of many people, we know that for every sufficiently small compact open subgroup K inside finite idyllic points of G, we get a nice algebraic variety, so smooth algebraic variety denoted by SH sub K over a number field, spec E, where E is a number field called the reflex field. Okay, it's determined only by the Shimura datum Gx, not by the choice of K. Right. So here, as usual, the complex points of this variety is identified with the double quotient GQ acting on diagonally on X times G of AF, and you mod out by K on the right. Okay. Right. So here, I mean, let me just briefly say in words, this X is a G of R conjugacy class of homomorphisms from the Deligne torus into G over R, and satisfying some axioms. So in particular, this X itself is a disjoint union of finitely many Hermitian symmetric domains. this is this. Right. Right, so so we're going to consider, just like in the modular curve case, you see that, so there you only get a nice answer by considering this compactification of the modular curve. So x naught n denotes the compactified modular curve. So here, it turns out that you only get a very neat expression of the Hasse-Weil zeta function if you consider the suitable compactification. So what we need to consider is the intersection cohomology. So let me simply denote by IHI. So this is the intersection cohomology of the Bailey-Borel compactification. Okay, so this is the Bailey-Borel compactification. Okay, and so to be even more precise, I'm considering the analytic version of this. So I'm considering the entire homology of this Bailey-Borel compactification base change to E bar, and with coefficients in the usual intersection complex. And I take QL bar coefficient. So here J is the embedding into the compactification. And let me just remark that for all I'm going to say, it's also okay to replace this constant sheaf QL bar here by any local system coming from a representation of the group G. Okay, so then on this IHI, you have commuting actions by simultaneously by the Galois, the absolute Galois group of E, and the Hecke algebra of K, of level K. So I have omitted the notation K here, but the Hecke algebra of level K and the Galois group, they act on here. And then, so the main, right, and it is known that as a Hecke module, this IHI has a nice decomposition. Right, so you can decompose it into a direct sum indexed by pi f of the k-fixed parts of pi f, tensor with some multiplicity space, which I denote by wi of pi f. So here, this is a Hecke module, and this is a Galois representation. And here, pi f is the finite part of some discrete automorphic representation pi. Okay. Right. So somehow this is already one important motivation for considering the intersection cohomology of the Bailey-Borel compactification, is that you actually, as a Hecke module, you can express it purely in terms of discrete automorphic representations. Right, so then, so somehow the main question is to understand what is the other part. So namely, so I define W of pi f to be the formal alternating sum over the degree I of these Galois representations Wi pi f. And I think of this as an object in the Grothendieck group of color representations of E. Okay, so the main question is to understand this object. Okay. All right. So here is a rough guess. So the rough guess is simply that this is given by W pi f as a color representation is given by composing some kind of global L parameter of pi with with this particular representation R sub x of the Langlands-Steele group, base change to E into some GLN. So here this thing is uniquely determined by the Shimura datum, so it's essentially the highest weight representation. Highest weight representation of weight given by the negative of the Hodgkin character of the Shimura datum. Okay, so if you base change over E, then, so I mean this thing is only a representation of G hat, but if you consider the L group over E, then it naturally extends to the whole L group. Right, so this is the rough guess, but unfortunately this is wrong, so not true. And the reason this is wrong is precisely because of endoscopy. So not true because of endoscopy. Okay. Are there any questions so far? Okay, so we need a correction of this rough expectation, and X is the Shimura datum. Yeah. So we need a correction, and so the correct conjectural recipe to describe this was given by Langlands and Kottwitz. So Langlands was able to find the correct formulation in a tempered case, and Kottwitz extended it to arbitrary pi. So correct conjectural recipe given by Langlands and Kottwitz. So this was roughly in the 1970s to the 80s. And so I'm going to recall this, this recipe briefly. And so this recipe has very similar structure as others multiplicity conjectures, similar structure as others multiplicity conjectures. Okay, so let me first briefly recall that. I'm going to swap these two modes. Okay. Right. So let me very briefly recall the structure of access multiplicity formula conjecture. So this roughly says the following. If you have some discrete automorphic representation, then it will actually lie in some global actor packet psi of G of A. So where this psi is a so-called global author parameter. And it's a certain map from the product of the global Langlands group of Q, which appeared in Professor Alice's talk yesterday, times SL2 into the Langlands dual group of G, satisfying some properties. And for such psi, you can define a certain set of representations of G of A, and this pi should be a member of that. And conversely, for an arbitrary member of that packet, conversely, if you have some member pi prime of this global author packet, then there is a recipe to determine whether it appears in the discrete spectrum and also what's the multiplicity that it appears with. So the recipe is basically, so this pi prime should give rise to, after some extra choices, maybe so in the case where G is quasi-split, you need to choose some Whittaker datum, and in the case where G is an inner form, you need to pin down more choices. But supposing all those are done, then this pi prime should give rise to a certain representation of the centralizer group. So let me denote by chi pi prime. So this is a representation of the centralizer group of psi, and for simplicity, throughout the whole talk, I'm going to assume that all my other parameters have the property that S psi is a finite abelian group. So I don't need to distinguish between representations and characters. All right, so you get a representation of this centralizer group, and this is actually built from a product over all the local places of representations of the same group, but only determined by the component of pi prime at V. And so the multiplicity of pi prime in the L2 discrete spectrum is equal to the multiplicity of a certain canonical representation of this guy, right? Chi canonical. So this only depends. So this chi canonical depends only on psi, not on pi prime. So you are looking at the multiplicity of this canonical guy inside this representation determined by pi prime. Okay, so that's the form of access multiplicity conjecture. So of course, if I assume that this is just a finite abelian group, then by this multiplicity, I mean either 1 or 0. Okay, so this is. I'm sorry? So as I said, so in general, if you want to, for example, to be unambiguous about this, you need to make some additional choices. Like if G is quasi-split, you need to choose a Whittaker datum. If G is an inner form of a quasi-split form, you need to make more choices. Oh no, but I'm just assuming that it's finite abelian for simplicity. Yeah, yeah, for simplicity. Okay, yeah. All right, so then this is the shape of the Arthur's multiplicity conjecture. And so the Lalanne-Skotowitz recipe for describing the Galois representation is very similar to this in flavor. But it involves slightly more ingredients. Okay, so here is the Lalanne-Skotowitz recipe. Suppose we start with some pi f, such that the scalar representation is non-zero. So this would already imply, so as I explained before, this pi f must be the finite part of some pi, which is a discrete automorphic representation. So again, this lies in some other bracket for some global A parameter psi, but it's only a representation of G of AF, so it's only the finite adelic part of this global A packet, right? And so then just as before, so here I explained that this representation chi pi prime is actually a product of chi pi prime v, where each chi pi prime v is a representation of S psi that only depends on pi prime v. So here you can do the same thing by multiplying over all the finite places v of chi pi v. Okay, so this I call chi pi f. Right, so then this chi pi f is a representation of S psi. So again, for simplicity, I'm assuming S psi is a finite abelian. Right, so you get this representation of the centralizer group. But somehow this only uses non-Archimedean information because I'm only starting with pi f, which doesn't have an Archimedean component. However, there's a subtle step here where you somehow need to add Archimedean information nevertheless. So one needs to use the Shimura datum X to cook up some canonical modification of this one. To get some modification. Which I denote by chi pi f tilde of chi pi f. Okay? Right. So in some sense, this chi pi f tilde is different from chi pi f, and the difference is given by this Shimura datum X. So this chi pi f, it doesn't see what the Shimura datum is. It's only an invariance of this finite adelic representation pi f, but chi pi f tilde also knows about the Shimura datum. Okay? Right, so this is the first ingredient. And the second ingredient is we also need to talk about the global L parameter. And so in this case, we can think of the global L parameter of the A parameter per psi. So we can compose the global L parameter of per psi with, so again, as before, with this representation R sub x. So what you get would be a finite dimensional vector space, let's say over QL bar. And it has two actions. by the global Galois group of E times the centralizer group S per psi. Okay, so this is what you would get. And this one, since it has these two commuting actions, you can decompose it according to the eigenvalues of S per psi. So you decompose it into according to eigenvalues of S per psi into the chi eigenpart, so V per psi chi. And so this is just a representation of the Galois group. And now the Langlands-Cortwitz recipe states that this Galois representation can be described as follows. So this W pi f is equal to, okay, let me state this as a conjecture. Conjecture. Okay, so right, so the pi f isotypic part in the intersection cohomology as a Galois representation is equal to the following. Take the sum over all possible psi such that your pi f appears in the global A packet, pi psi, G of AF. And then you sum over all the possible chi, all the characters of S per psi. Okay, and then you look at the multiplicity of chi in chi pi f tilde. So this is a number which is either 0 or 1. And then you multiply it with a sign plus minus 1. And this sign depends only on psi and chi. This depends only on psi and chi, not on pi f. And then you multiply by the scalar representation V sub psi chi. Okay? Yes?
So all your psi are locally equivalent in almost all places? Because
Locally
equivalent.
Locally equivalent.
Because
Oh, yes, yes, right, yeah, sure, yeah. Right, yes. That's right, yeah. So in most of the practical situations, this psi is unique, actually.
It's unique with just one element.
Yes, so in practical situations, for all the groups that we can actually prove this, this psi is uniquely determined by pi f.
Are there any examples where you have multiple psis?
I'm actually not totally sure. Yeah, but theoretically, you need to take this sum. Okay. Say it again? Well, so I mean, basically, I mean, a priori you said. Okay. I see what you're saying. So, right. So in the, okay. So maybe there's, right. So maybe, right. So I think, yes, right. So plus some cohomological condition. On psi infinity. Is that okay? Yeah, so, yeah, but in practical situations, you don't actually need to impose this because psi is already determined. But yeah. Okay, so this is kind of the goal of the subject, and Right, so no, so here what I mean is, right, so actually it's related to your previous question. So here one must impose some cohomological condition on the Archimedean component of psi. So then conjecturally this psi, which is a map from the global, the Langlands group of Q times SL2 into the Langlands dual group, when you restrict it to, so in the usual diagonal way to the Langlands group itself, it should factor through the Galois group. So that's what I mean by the, yeah. Right, so this is only true after you impose some cohomological condition on the Archimedean component. Right. Okay, so the main result I'm going to state okay, it's the following theorem. So this is work in progress in collaboration with Mathématiques and Guillaume. So I'll first state the result and then make a lot of explanations. So part A is we basically, okay, so we define W sub C of pi f using the compact support cohomology instead of compactly supported cohomology instead of the intersection cohomology of the Bailey-Borel compactification. So then for the unitary Shimura varieties, of the form G is equal to the restriction of scalars from some totally real field F of some unitary group U. So here F over Q is a totally real extension, and U is so to to emphasize, it's an honest unitary group. If you don't know what that means, it probably means you already know what I mean. So if you don't know what I mean by honest unitary group, then the notion of unitary group you have in mind is what I want to present. Okay. Okay. Right. So so use an honest unitary group with respect to some CM extension F tilde over F. And here an important assumption is that this F is not equal to Q. Okay. But we still allow arbitrary signature. Okay. So here the funny thing is we make this assumption, but we don't use this assumption in order to make the Shimura variety compact. So we allow arbitrary signatures. We don't impose that there must be one real place where the signature is definite, which is the usual condition to make the Shimura variety compact. So we do consider certain non-compact Shimura varieties, but we don't allow F to be equal to Q. Okay.
Why can't you let F be
Hmm?
So why not?
Okay, I'll explain later. Right, so under these assumptions, so for this Shimura variety, we prove that that the conjecture of Langlands-Kottwitz is true with W pi f replaced by WC pi f. Okay? Right, so this is part A. And part B is that for the same Shimura variety, actually this replacement is unnecessary. So W pi f is equal to WC pi f in the Grothendieck group. Okay? All right, so to briefly answer Yuji's question, the reason we assume this is because if you don't assume this, then you actually don't expect this conjecture should be true under this replacement because you don't expect B to be true, right? So you see that somehow in this particular situation, we have divided the proof of the conjecture into two steps. One is we first prove it by replacing W pi f with WC pi f, and second, we prove that they are actually the same. Okay, so I want to leave this main result. And now I'm going to make a bunch of explanations. I think I can use this part here. Okay, so some explanations. So firstly about part B. So note that by purity, we know that the intersection cohomology has purity. So even though this thing is defined as the alternating sum over the different degrees, there is actually no cancellation. So it has no cancellation. Which means, in principle, once you know what this alternating sum is in the Grothendieck group, at least in principle, you're able to recover each degree by just separating the Frobenius weights, right? So this is by purity. So that's why when we consider the problem with intersection cohomology, it's harmless to take the alternating sum. However, this is not true for the compact support cohomology. Okay, so this means part B doesn't imply that compact support cohomology and intersection cohomology agree at each degree. Rather, it's a statement about cancellation. So the intersection cohomology has no cancellation, but the compact support cohomology has some complicated cancellation to the effect that after the cancellation, they become the same. Okay. And so another remark was that, right, so this is a generalization of a result by Berlinski and Lebesgue in 1984, where they proved a similar result for the Hilbert-Blumenthal case. Okay. Okay, so this is all I want to explain about part B. And so part A will take more explanation. Okay, so for part A, I need to explain two things. Firstly, you see that even in the formulation of the Langlands-Kooltwist conjecture, we need the concept of other parameters and other packets, and also the association of these representations of the centralizer group attached to each member of the A packet, and so on. So in general, of course, all these are conjectural, but in this case, it's unconditional modulo some ongoing work. So here, for this unitary group G, the honest unitary group G, A parameters, A packets, etc. Are constructed in the work of Mock for quasi-split unitary groups and extended to inner forms in the ongoing work by colleagues at Mingus, Xin White. Right. Yeah, so this is usually referred to as endoscopy classification for the unitary group. And note that for this sort of question, it's actually very sensitive to the center of the group. So you're not allowed to say, well, you have this result for the honest unitary group, then you can also deduce the same result for unitary simulated group, or maybe even some more strange variants of that by changing the center. So in particular, right. Yes, yeah.
So there's no Galois group.
No Galois group, right. Yeah, but so I'll come to that in maybe 2 minutes. So for instance, you may want to ask, how about the PL type Shimura varieties? And so in that case, you can also talk about unitary Shimura varieties. So I'll say PL/unitary. So there, the group G is no longer an honest unitary group, but it's some variant of the honest unitary group with a different center. So for this one, so I mean the above results do not apply. Okay. So in my understanding, if you are considering unitary groups of an odd number of variables, then it's relatively easier to go from the honest unitary group to the other unitary groups. But if it's an even number of variables, it's actually a very subtle question. So, so you see that in some sense, even for the sake of being able to apply these results, we are forced to consider the honest unitary group G, not some PL unitary group. And for this G, so for this honest unitary G, the Shimura variety is of abelian type, not PL type. The Shimura variety is of abelian type, not PL type. However, yeah, and also it turns out that for some recent progress in certain arithmetic applications, it's actually important to prove this theorem for the honest unitary group G. So I don't really have time to talk about those applications, but it just turns out that the honest unitary group G is sitting at a really sweet point where you can simultaneously apply these results on endoscopic classification and also find applications. Okay. Okay, right. And then, so how does the Galois group enter the picture? Oh, okay, I don't want to erase this. Okay. It just means you have a Hermitian form, and you look at all the automorphisms of the vector space preserved in the Hermitian form on the nose, not up to some scalar. So there are two usual variants of that. One is you allow the automorphism to preserve the Hermitian form up to some scalar, but the scalar can be an arbitrary element of the field F. But you can also ask that the scalar must be in Q cross. So there are these two variants. And the second variant is the PL unitary. Right.
Is it possible to understand each WI, each of this image in Gaussian?
Yes, so as I explained, once you have this result, you can actually read out with each WIS by just separating out the Frobenius weights.
Yeah, but if the WI itself is reducible as there is some extensions.
Oh, then, yeah, so then there's the question of semi-simplicity, and that's not treated in my work. But there is some ongoing work by some other people which study this question. Okay, and so the second point I want to explain about part A is what do we mean by the global L packet? The global L parameter of an isoparameter for psi. So what's the meaning of that in this context? Right. So in the context of, let's say, in the context of Mach and KMSW, a global A parameter per psi is essentially some combinatorial datum coming from, well, I shouldn't say combinatorial, so it's some, so it's essentially built from conjugate self-dual cuspidal automorphic representations pi I of GLNI over this CM field F tilde. And it turns out that if psi contributes to the intersection cohomology, then each pi I turns out to be essentially regular algebraic. And each pi I is regular algebraic after a twist. Okay, so this is basically some easy argument tells you this. And then we can see the Galois group now by this famous theorem due to a long list of people, including Labesse. And the history of this theorem is very complicated, so I'm going to list the names in alphabetical order. So, Chenavier, Cauzel, Harris, and many of them are here. Kottwitz, Labesse, and Shin, and Taylor. Okay. Right, so this says that this pi I has an associated Galois representation of the CM field F tilde. So essentially built from these associated Galois representations of the pi i's, the desired global L parameter of psi. Okay. So one builds from these Galois representations the so-called global L parameter of psi. So here one also needs to use a result by Belaish and Chenavier. Which is in some sense to ensure that you can actually extend this Galois representation from F tilde to F. And then essentially by Shapiro, because G is the restriction from F to Q of the unitary group, so if you have a Galois representation of the Galois group of F valued in the L group of the unitary group, then you get a Galois representation of the Galois group of Q valued in the L group of G. Okay. Okay. Right, so this explains all the ingredients in the statement of part A of my theorem. So are there questions? Hmm?
I have a question about the earlier remark. So you said you wrote an initial guess and said that this was not true because of endoscopy.
Right.
You wrote the corrected one. I couldn't see in the corrected one the reference to endoscopic.
Well, I mean, so in the corrected conjecture, which is on the top part, it basically splits this representation v psi into v psi comma chi, where chi runs through characters of the centralizer group of psi. And each part may appear with a different multiplicity. So that's the phenomenon of endoscopy. If this psi is stable in the sense that there's no endoscopy, that means S psi is trivial. So then there's no splitting of v psi into parts.
S psi stands for the component group, right?
Yes, the component group of the centralizer group of psi. So if that group is trivial, then there's no splitting, so then it agrees with the naive guess. And if it's non-trivial, then v psi splits into these different parts, and each of them can appear with a different multiplicity. Okay. All right, thanks for this question. Okay, and so now I have 6 or 7 minutes left. I'm going to tell you a little bit about the structure of the proof of part A only. Structure of proof of part A. Okay, so the first step is you want to so essentially just count points mod p. So for almost all primes p, this level k is hyperspecial at p. Okay, so kp inside G of qp is hyperspecial. And so we want to count the mod p points. Count mod p points of a in a suitable sense a good integral model, p-adic integral model of the Shimura variety. Step 2 is you want to compare the resulting one right. So I mean, essentially we're looking at the compact support cohomology. So by the Grothendieck-Lefschetz trace formula, in order to compute the trace of a Frobenius and the Hecke operator on the compact support cohomology, you just need to count points. But then, so you get some result counting these points, and we want to compare the counting result with the stable trace formulas. With the stable Hausdorff-Selbel trace formula for all endoscopic groups. Okay, so this is an interesting thing that happens to Shimura varieties. Namely, the result of the point counting cannot be compared with any trace formula for G itself. It has to be stabilized and then be compared with the stable trace formulas for the endoscopic groups. So somehow the theory of endoscopy is just everywhere in this subject. And okay, this is the structure. Okay, and then the third part is to apply some suitable spectral expansion of these stable trace formulas and then go back to G. So apply spectral expansion of these stable trace formulas for H and go back to H are the endoscopy groups and go back to G. Okay. Right, so this is the step where we need the input of endoscopic classification. Okay. Right, so this is the rough structure of the proof. And for steps 1 and 2, we actually proved them quite generally. So this was a theorem joined with the same collaborators in 21. So steps 1 and 2 are okay for all Shimura varieties of abelian type. Okay. Right, so in the, okay, I still maybe have 1 more minute. So I'll state another theorem in the near future. So this is joined with Tom Hayes, Yihang Zhu, in progress. So we check that steps 1 and 2 are okay for paraHoric KP. Under the assumptions that you need abelian type, you need P is not 2, and G should be quasi-split over QP. Quasi-split. And and the adjoint Shimura datum should have no factor of type DH. Okay, I think that's all I want to present. Thanks.